Okay, I don't know what this is about. It took 20 years, but we finally found it from Up and Atom. Let's see.
What you're looking at is a signal scientists have been searching for over 20 years. It's a direct message from the nucleus of the isotope thorium-229. And in a breakthrough, they've finally found it. Why have they been searching for this? And what does it mean now that they've found it? This could help unlock the fundamental laws of the universe. You might not know this, but it's long been suspected that the fundamental constants of our universe, those foundational numbers we assume never change, are
Right.
actually changing by tiny amounts. If they shift, even slightly, it could transform our understanding of physics, giving us clues about dark matter, extra dimensions from string theory, or even a fifth force. Scientists have been trying to measure changes in the fundamental constants for decades, but our measuring equipment hasn't been sensitive enough. But now this signal is the key to creating the world's first nuclear clock, a device precise enough to detect changes that
Oh boy, there's too many ads nowadays.
New Lux Cravings boxes from
There's way too many ads nowadays. Wow.
been impossible to measure. Once it's complete, this clock could open a gateway to new physics, challenging long-standing theories about our universe. In this video, we'll discuss this discovery and its implications for science, but before we dive in, let's quickly recap. What are fundamental constants and why do they matter so much? Fundamental constants are fixed numbers that exist in the universe.
Right.
They set the stage for how the laws of physics work. Some examples are the speed of light, which places a limit on how fast we can travel or send information. Boltzmann's constant, which governs the relationship between temperature and energy. And the gravitational constant, which dictates how strongly two masses attract each other.
Also, these constants, I'm not sure all of them, might be all of them, they haven't been derived. They can only be measured, which again is a indication that we don't know where they come from. So there's definitely some underlying physics that we don't understand.
Through gravity. Physicists have boiled down the fundamental constants that shape our universe to just 26 numbers. Our current theory of known matter, the Standard Model, treats these numbers as unchanging in both space and time. The funny thing about fundamental constants is that they can't be predicted from theory. That's what makes them, well, fundamental. They have to be experimentally measured. Nature kind of just has to tell us what they are, and no one knows why they have the values that they do. As far as we know, these numbers are just written into the fabric of the universe. Even though they're a bit of a mystery, the constants aren't causing any trouble. Or so we thought. Theories are starting to arise that are making scientists question the constantness of the constants.
Right.
Theories linked to some of physics' deepest unsolved problems. For example, they couldn't help but notice that many of the constants have the exact perfect values to support life. If some of them were off by even the tiniest amount, life as we know it probably wouldn't exist.
Right.
Take this one, the fine structure constant.
No, it's true. There's a lot about the evolution of the universe that is very puzzling. And so there's a really good book I read fairly recently called Origins of Time. It was the last book written by Stephen Hawking with his last student, essentially written by his last student. And there's a bit of a roller coaster, but effectively it's a very compelling theory or argument that since we are not separate from the universe, most of physics over the last few decades has assumed that we are capable of writing laws that are objective, but because we are within the universe, writing these laws in the universe, even our theories themselves are subjective in a nutshell. And so one way to kind of explain how is it that life arose, how is it that the universe expanded just the right amount at the right time and then slowed down just the right time and then sped up again, for no known reason. And it's sort of postulated that it's because the laws of the universe themselves are geared towards life or consciousness. And so, in some ways, it's this big quantum wave equation where the measurement is being done by us. So it's this epic delayed measurement quantum entanglement experiment. And so in some ways, we sort of consciously will the universe to exist. And so it exists. And so there's no reason at this stage to believe that the universal constant should be constant. So wouldn't be such a remarkable find.
It's not as famous as some of its constant cousins like the speed of light, but it's a favorite among scientists. Richard Feynman once said, "All good theoretical physicists put this number up on their wall and worry about it." It combines the electron's charge, the vacuum permittivity, Planck's constant, and the speed of light, and has the value of about 1 over 137. Just like the gravitational constant tells us this.
Was it 1 over 137 or was it sort of 1 over 137? So it's been a while, but all these constants. I think it was sort of 1 over 137.
Strength of gravity. The fine structure constant tells us the strength of electromagnetism. It's a pretty big deal because electromagnetism affects, well, electricity and magnetism, which is also light, friction, and basically all of chemistry. Now what's crazy is that its value lies in a perfect sweet spot. It's strong enough to bind electrons to the atom's nucleus, but loose enough to let them whiz around and interact with other atoms, performing chemical reactions, which are kind of the basis of life.
So that's the kind of argument against the multiverse theory, which is, most of, like, the Marvel multiverse is just, for me, it just feels like garbage. It's not really understanding how even the proposed theory works. But even according to this, like, why is it that this constant lies in the Goldilocks zone? And according to, I guess, Hawkins' last proposal, it's because that's what life requires it to be. And so the entire wave function, all of the multiverses collapse around this. So it doesn't mean that we have all of these other universes or multiverses where there's no life. It's just the wave function collapse, so they don't exist.
If alpha were just a tiny bit weaker, electrons wouldn't bind to the nucleus at all. But if alpha were just a tiny bit stronger, electrons couldn't move freely and no chemistry would happen. It seems to lie in this perfect Goldilocks zone for life to exist. How did that happen? Why is our universe so perfect for life to exist? Well, a theory that's been proposed to explain this puzzle is if the constants vary in space and time, and life appeared in a part of the universe where the constants were the exact right values to support life. That would explain the extremely improbable chances of us being alive to measure them. Another reason some scientists think the constants might vary is because of newer theories of physics, like string theory, which tries to unify gravity and quantum mechanics, one of the biggest unresolved challenges.
So the strong theory, based on experimental evidence, that the fundamental constants do not vary in space. They might vary in time, but not in space, and that's the background cosmological radiation, the CBR, cosmological background radiation, which is uniform and equal anywhere that we look, from within our planet, from within Earth, as far as we can get. When we look around and measure in any direction, it's uniform and the same. Like it's as same as we can measure, and that indicates that if there was a Big Bang that we assume, wherever we look, that's where it happened, and it happened uniformly. So it was a uniform sort of soup expanding or exploding, and if the constants were different, we'd probably measure a different CBR everywhere, but it's the same. So that's why we believe it's the constants are the same everywhere in the universe. But it could be also that the universe is significantly larger than even what we currently think, and all we're seeing is the CBR from our part of the universe, and that there are other parts that are much farther away where the constants could be different. So anything's really possible.
Challenges in physics. These theories involve extra spatial dimensions to our current theories, and we would perceive changes to these.
So just kind of put it in perspective, right? Like the Hubble telescope, right? I mean, this is something that really blew me away, right? The mission duration was 34 years, 10 months, and 20 days, right? It launched in 1990. Okay, and even for me, it's I always think it launched a lot further back in time than it did because of that one story where it's not a story because of what actually happened, which is that before Hubble went up into space and took images of the universe, we did not actually know how large the universe actually was. We didn't know how many galaxies there were. And we thought that probably it was as big as, about as many stars that we could see with our naked eye. And when Hubble went up and looked, as far as it was able to magnify, it saw as many galaxies as we saw. And so effectively it saturated even its capacity to see how big the universe or how many galaxies there were. And so it's not that the universe was a magnitude or magnitudes bigger than what we had imagined. It was magnitudes of magnitudes of magnitudes. And that got even expounded with the Webb telescope, that the universe is so much bigger than we had ever even imagined. And how big that universe is exactly was significantly different because of Hubble. And that's only 30 years ago. Only in 1990 we hit that realization. So, science and physics is evolving very fast. And so you should really challenge anyone who says like, oh, we mostly understand physics other than a few things here or there. It's not true. There's a lot that we don't understand, and anything can happen. So only in 1990 did we even know that the universe was significantly bigger and more populated than we ever imagined.
Spatial dimensions as the fundamental constants changing. And the final theory that the constants might be changing comes from the study of dark matter. Dark matter is the mysterious matter that accounts for over 20% of the universe's mass, yet we know almost nothing about it. Some physicists think that dark matter interacts very weakly with an atom's electrons or nucleus, causing alpha to drift or oscillate by some extremely tiny amount.
Again, dark matter is a theory. We don't know that there is such a thing as dark matter. It's a theory in order to explain why galaxies hold together. So galaxies, the rate at which they're spinning, should just fly apart, but they don't. They stick together, and so the only way that we can model that with mathematics and theory is to inject dark matter, add mass that we can't see or measure, and that would provide the gravitational glue to keep galaxies in the form that they are without just spinning apart. That's what it is. So we don't know that there is such a thing as dark matter. It's just, again, a fudge factor that we put in the equations, and we try to explain that fudge factor by saying, oh, it's possibly dark matter. So to talk about dark matter like this is a little bit, we have never measured dark matter other than the fact that galaxies do not fly apart.
If we observe this drift, it could help us understand dark matter. What's amazing is that we actually already have some indication for variations in alpha. In galaxies far, far away, there are super bright objects called quasars. These are supermassive black holes that suck in gas like a whirlpool. As the gas gets sucked in, it heats up due to friction, and this makes it shine super bright. In fact, quasars are some of the brightest objects in the universe. To measure variations in alpha, we can look at the light coming from distant quasars.
So a quasar is essentially a collapsed star that never quite made it to a black hole. So it was a star that was big. It ran out of fuel and started to collapse. It's a supernova, and the end result of a supernova is either a quasar or a black hole. And it wasn't big enough to collapse completely into a black hole.
Quasars so far away that their light took several billion years to reach us. How? Well, as their light heads toward Earth, it runs into gas clouds along the way, which absorb some of the frequencies. The light frequencies that get absorbed depend on alpha. So if alpha were different in the past, we can detect a change in it by comparing the absorbed frequencies from the past to current frequencies. So what did scientists find? Well, different research groups came to different conclusions. A famous experiment by the John Webb team did observe small variations in alpha, but other research teams who performed similar experiments observed no variation at all. So the evidence is inconclusive. We need more precise measuring devices and perhaps even an entirely new method. That's where this discovery comes in. It's the first step in building something scientists have been trying to build for over 20 years, a nuclear clock. A super accurate measuring device and our best bet for measuring variations in the constants. Cool, so let's get into what a nuclear clock is and how the scientists made this discovery. I know some of you have been thinking, nuclear clocks, don't we already have those? And the answer is no, we have atomic clocks. They're different, and I'll explain what the difference is. Understanding nuclear clocks will be easier if we first understand atomic clocks anyway, so it works out. But before we get into that, I found out about this nuclear clock breakthrough because I like to keep up with the latest science news. And a news website and app I've been using for a while to help you land they're dead. Interesting how the same event can be reported in such different ways depending on who's telling the story. Everybody or bias highlights specific differences in story and get the full picture. Ground news allows transparent. Understand?
World, the time is.
Oh, wow. There's advertisements everywhere, man.
Keeping time is our most precisely measured physical quantity, more than even length or mass, and atomic clocks are our best timekeepers. Their precision made scientists think they're our best bet for detecting changes in fundamental constants like alpha. But how, you ask? The fine structure constant has nothing to do with time, and neither do a bunch of the other constants. Well, to understand, we need to understand what an atomic clock is and how it works. A key ingredient of any clock is a regularly repeating event, like the rotation of the Earth, a swing of a pendulum, or the oscillation of a quartz crystal in a watch. This repeating event serves as a reliable tick. But the annoying thing about these clocks is that they can be affected by the environment. Temperature, pressure, and humidity can affect their ticking rate. Their components can break down over time. Even their size and shape can affect how they tick. These problems make these clocks unreliable timekeepers. But atoms have a very reliable way of ticking. From quantum mechanics, we know that the electrons in an atom are restricted to specific energy levels. You can think of them like rungs on a ladder, a wonky, uneven ladder. An electron can jump between any two levels, but can't land in between them. The electrons jump by absorbing or emitting light at very specific frequencies. The energies of these light frequencies correspond to the size of the gaps between energy levels. And the higher the frequency, the higher the energy. For example, blue light has a higher frequency than red light, so blue light has higher energy. Atomic energy levels are extremely stable since they're set by the literal laws of nature. They don't change according to pressure or temperature or where they are in the universe. And because the energy levels are so stable, so are the transition frequencies. We can count out a specific number of oscillations of a particular frequency and use those counts as a reliable tick of a clock. For example, the basic unit of time, the second, is defined as the amount of time that passes after 9,192,631,770 oscillations of a certain transition light frequency from a cesium-133 atom. Because of an atomic clock's stability and the fact that identical atoms under identical conditions are essentially the same, using an atomic clock is more fundamental than a pendulum or a quartz crystal. To put an atomic clock's accuracy into perspective, a cheap quartz wristwatch might drift about 15 seconds in a month. But the most accurate atomic clock in the world, a strontium-87 clock, drifts by only 1 second in nearly 40 billion years. That's almost 3 times the age of the universe. Now here's the cool part. Just as absorption frequencies from quasar light depend on alpha, so do an atom's energy levels. Remember how alpha is the strength of
Well, the age of the universe according to our current theories.
electromagnetism? It therefore influences how close the negatively charged electrons hang around the positively charged nucleus. So if alpha changes with space or time, the electron energy levels in an atom will change too, which will change the transition frequencies. By measuring changes in these transition frequencies, we can measure changes in alpha. Scientists have actually already tried to do this, and once again, there were problems. An experiment performed in 2018 did observe a fractional change in alpha of about 1 part in 100 quadrillion per year. This result means that if the value of alpha is changing, it's doing so extremely slowly. It would take 100 quadrillion years for its value to double. Okay, but even though they observed alpha's not changing much, it's still changing, right? Well, not exactly. Every measurement has some uncertainty called the error range, which tells us how much the true value might differ from the measured value. When we're measuring everyday objects, small error ranges usually don't matter that much. Who cares if a measurement is off by a quadrillionth of a meter? But when the objects are very, very small, error ranges can become significant. In this case, the error range includes 0, which means it's possible that there's no change in alpha at all. Once again, the evidence neither confirms nor denies a changing value of alpha. About 20 years ago, physicists started thinking about how to use a different part of the atom to make a clock, the nucleus. Just like an atom's electrons have energy levels, the atom's nucleus has energy levels too. But they're a bit different from the electron's energy levels. Inside the nucleus, there are 2 major forces at play. The strong nuclear force, which holds the protons and neutrons together tightly, and the electromagnetic force, which threatens to blow the nucleus apart because the positively charged protons repel each other. The balance of these 2 forces set up energy levels. But wait, why would a nuclear clock be more precise than an atomic clock? Well, even though atomic clocks are vastly better than regular clocks, they still have some problems. They're sensitive to unwanted stray electric and magnetic fields, which shift the clock's energy levels. And although they're much, much less affected by temperature than regular clocks, they're not completely immune. The nucleus, on the other hand, is sealed within the atom, shielded from the outside world by the electron cloud, so it's much less sensitive to unwanted electric and magnetic fields and temperature. Scientists estimate that nuclear clocks could be 10,000 times more sensitive to changes in alpha than atomic clocks. But there's been one major hurdle. Nuclear energy transitions are really, really big. This is because the strong force holds the protons and neutrons together so tightly. Nuclear transitions are usually about 1 million times greater than the transitions of an atom's electrons.
Right.
They're so large that no modern laser can reach the energies needed to excite them. The technology simply hasn't been invented. Bridging these nuclear energy transitions requires gamma rays, the highest energy light, where no modern laser can go. But in the 1970s, scientists made a strange discovery. By a lucky coincidence, the electromagnetic and strong nuclear forces in the thorium-229 nucleus are balanced so that one of its transitions is way smaller than all other nuclear energy gaps, about 10,000 times smaller. This energy lies in the ultraviolet range, placing it within the reach of modern lasers. In 2003, when scientists first started to think about how to build a nuclear clock, thorium-229 was the perfect candidate. Wait, did I just say 2003? If they found out about thorium in the 70s and they've been trying to build a nuclear clock since the early 2000s, and we're in 2025, that's over 20 years. If it's so important, why haven't they built it yet? Well, it turns out exciting a nucleus is really hard. There were a handful of engineering challenges that had to be overcome, spanning across nuclear physics, laser physics, quantum optics, and material science. The main problem was just knowing where to look. People knew the transition was small, but they needed to pinpoint the exact size before they could even begin building a clock. Guessing and adjusting a laser's frequency to match a transition whose size you don't know is like shooting in the dark. It'll take ages. But in 2023, CERN pinpointed the transition's energy. It was about 8 electron volts, which corresponds to a wavelength of about 148 nanometers. This discovery set into motion a flurry of 3 major experiments, all in 2024. In April, a team from Germany and Austria were the first to excite the transition with a laser. In July, scientists at UCLA confirmed the result, improving the CERN frequency precision by a factor of 1,000. And in September, a third experiment made a breakthrough when they measured the transition using a special custom-built ultraviolet laser. The frequency cone laser allowed them to be 1 million times more precise than the previous 2 experiments. And that's what this is. The long sought after transition frequency from the thorium nucleus. It's a frequency of 2,20,407,384,335 kilohertz, plus or minus 2 kilohertz. This is an exciting first step towards building the world's first nuclear clock and potentially rewriting the laws of physics. A huge thank you to my patrons on Patreon who make these videos.
Well, I felt like it ended very suddenly. Yeah, it would have been nice if she had done like a little, summing it all up together, just talking about the numbers and looping it back to alpha, so the atomic constant. That would have been nice.